Hi everyone, it's my pleasure to introduce Professor Stefan MANDT for today's lecture. And Stefan is an associate professor at UC Irvine and also one of the lead PIs. And I'm honored to say that he's also my advisor. And Stefan is an expert in machine learning and generative models. And his work links the theoretical aspects of these models to applications across multiple scientific domains, including climate science. So,
yeah, thank you for the kind introduction, Francesco. It's great to be here and nice to see all the friendly faces. Yeah, title of my talk today is Scientific Inference with Diffusion Generative Models. And the main idea is roughly like that, right? Diffusion models are typically mainly used for visual content. We've seen a lot of progress for sort of image generative models, right? Artifact removal of various sorts, super resolution, video generation, and so on and so forth. But what if we could kind of tailor and target diffusion models in such a way that they become reliable instruments for scientific instrument and particularly for scientific questions and scientific inference, right? So in other words, can they be made or converted into reliable statistical tools for data analysis? And this is very much the talk that we will discuss today. To say like the same thing in a little bit more detail, right? So current diffusion models, they largely focus on things like photorealism, which could be measured by MANDT scores, et cetera, et cetera. But in science, for example, scientific imaging, we oftentimes focus on other sort of more nuanced characteristics. For example, reflecting the measurement process of a physical system, right? I mean, if you could exactly model the microscope, or if you could exactly model the telescope or the measurement device that you use to record the data, can you then maybe sort of invert it exactly, or at least as good as possible, to ultimately make to reason about the underlying state of the world, right, that you care about. In other applications, we not only care about like getting the mode of the data right, but we really care about the tails of the distribution, right? In particular here in weather modeling, this is very relevant, right? When we do, for example, precipitation super resolution, then oftentimes, you get these spatially resolved images of rain pockets, right? And oftentimes the rain pockets are very intense, but if your model doesn't capture the tails right, then it will actually dramatically underestimate these sort of extreme events. And if you look at the marginal distribution over rain, this is really something we should capture reliably, right? And that's not what current diffusion models do. And then finally, in other many applications, including climate and weather, we really also care about not only the mean prediction, but also the corresponding uncertainty around it, right? So for example, in scientific imaging or in astrophysics, you might want to know the image that is super resolved, did I just hallucinate a star or a galaxy, or with which probability can I really say that this is a star or a galaxy, right? So it's not only about generating beautiful images, it's really about the underlying statistical guarantees, right? And so we need to revisit all of these existing models along these sort of more sort of statistics-inspired or sort of natural science-inspired lenses. And so in this talk, I will try to cover a variety of recent papers that all kind of span this space that I just outlined. And in particular, I will talk about these three different aspects. I will talk about controllability, which is all about improving the test time control of diffusion models, right? How can you do inference with diffusion models better? I will also talk about the expressiveness of these diffusion models. For example, can we make them to correctly capture tail statistics of our data? And then finally, I'll talk about calibration, which is this angle of uncertainty. Can we make diffusion models such that they give credible uncertainty estimates for reliable decision making? Okay. And since this entire talk is about diffusion models, I'll first cover some common ground here. And I realize this is a fairly technical audience. I've actually removed a lot of the technical details here, which you probably would be very good at understanding, but maybe it still helps to kind of get a presentation on a more higher level. So let's talk about the diffusion process. So I'm pretty sure that many of you have already used diffusion models in your everyday work, but what is it again? Well, it's a model that starts with sort of noise-free images, Then you add noise to it at various lengths or at various intensities until you completely destroy all information of the image. And then you try to successively train a model to successfully undo it, right? So you have a probabilistic denoiser that you apply iteratively at various noise levels, such that when you apply it on data, right, you start with pure noise, it starts to interpret patterns in the data and tries to successively refine these patterns more and more until you sample something that resembles an image. Now, in this talk, I will assume a statistical, so namely a sampling from the data distribution, right? So what you see here is a distribution in blue that's supposed to be the distribution of natural images. And basically what diffusion models do is that they learn the score function, which is the gradient of the ground truth log probability density of your data, right? Try to approximate that as well as possible. And once you've learned this vector field, it actually, all you need to do is to kind of follow it, right? But also perturb your path. Otherwise, we would just kind of collapse to the most likely single image in the data set. But if you perturb it with a little bit of noise, it turns out you exactly sample from that distribution. So you can think of this as effectively constraining the search space through the score. And then there was actually just like a few days ago, I think actually somebody here presented a very nice view on diffusion models essentially following Langevin dynamics, right? And that is exactly this algorithm that kind of performs gradient descent on the log likelihood of your data distribution, but perturbs it with noise, and then you're basically guaranteed to sample from that distribution. So the endpoint of this operation then needs a sample, and hopefully that sample resembles a sort of plausible image. Now, if we only did that, right, only unconditional generation, it would be a pretty boring world. We would basically just kind of create random images, right? But that's not really what we want. We want to be able to control our diffusion process. And oftentimes we don't know upfront in which way we want to control it. So we want to kind of think about algorithms that allow us to control the diffusion process, in particular at test time, right? In a way that you haven't explicitly prepared the algorithm to operate for. And this is called guidance. So the main idea is roughly as follows. We have a pre-trained diffusion model, right, that basically has learned to sample from P of X. But this time we kind of put on our Bayesian statistics hat on, and we can think of that as a prior distribution, right? It's the distribution of all natural images that you've seen, or it might be the distribution of all sort of weather images that you have seen before. Now, we also need another loss, or you can think of it as a classifier, P of Y given X. Now this, if you care about generating cat images, this could be an animal classifier, right? Where you specify the label Y to be cat, right? Let's imagine that this is also given to you. And it turns out, if you simply combine these two terms, if you combine the learned score of your diffusion model and you add the gradient of this log classifier with respect to its input, then this, again, effectively constrains your search even further, and you sample from this boundary region, which you can think of the intersection of the two, right? So in other words, in this case, you would sample from all natural images that are compatible with the label cat. Okay, so far I assume no questions. Okay. Now, in reality or in science, it oftentimes turns out that classifier guidance might be not of most interest. What we care about oftentimes in scientific imaging is actually what's more like related to artifact removal. And so in this case, it turns out that this, what I called classifier, the P of Y given X, is actually not so often a real classifier. It could be something else, right? It could be another model. But for now, I would just call it a guidance model. And in particular, in this context, oftentimes we care about so-called inverse problems. Can you raise your hand if you heard about sort of inverse problems? That's a familiar notion to you? Yeah, I think at least half here. So what are inverse problems? Well, you can think of them as basically undoing a lossy degradation process, right? And you can think of this as super resolution, right? The degradation that you undo here is sort of downscaling your image resolution. In painting, right? Maybe somebody has erased certain pixels as shown here, and you want to backfill like the destroyed information in the image. Deblurring is another example of an inverse problem, right? Over-saturation, if your image is too bright, right? This would be solved using inverse problems. Or, for example, all sorts of problems in scientific imaging. And it actually turns out there's a beautiful benchmark paper here by largely by colleagues from Caltech, from which these figures are taken. There are examples from black hole imaging, from kind of wave optics, simulation of Navier-Stokes equations, et cetera, et cetera. Okay, so so it turns out that, again, in all of these cases, we need versions of classifier guidance. But it turns out that there is a technical problem that makes it actually non-trivial, right? The main idea is that classifier guidance, if done naively, oftentimes works poorly in practice. Now, the reason here is a technical detail, right? When you do classifier guidance, I told you that you need to take your classifier, P of y given x, and then you differentiate it with respect to its input and add that to your score. But if you pay close attention to that, you actually need the classifier evaluated at x at various noise levels, not only at the clean image x0, right? So you need kind of P of y given xt and not P of y given x0. So how are these two connected? Well, they're connected through this formula, right? You take, so P of y given xt is essentially the convolution or the integral of P of y given x0, your noise-free classifier, times P of x0 given xt, in other words, the posterior distribution over noise-free images given your noisy image. And then, sorry, this should be actually integrated over x0 here, yeah? So integrate over all possible images that are plausible reconstructions, you plug them into your classifier, and then the marginal of that would be the object that you need. Now, as you can imagine, for those of you who have dealt with approximate inference before, right, oftentimes these high-dimensional integrals, in this case over pixel spaces, are not really easy to deal with, right? I mean, for example, you can take a unimodal approximation of this integral, like a point estimate. This would be based on Tweedy's formula. There's sometimes quadratic approximations to that work a little bit better. But it turns out that none of these approximations work really, really well, right? So all of these are fairly aggressive. And then the question that we asked ourselves in this case was, can we fundamentally rethink classifier guidance and maybe come up with a formulation that does not require any of these sort of potentially aggressive approximations up front? Yeah? Yeah, and so this actually leads to the first paper, which we just published at ICML this summer. As you can see, the other two papers that I'm going to talk about, they're all fairly recent. They're all from the last few months. But the first one I want to talk about is variational trajectory guidance, which solves this problem of needing to approximate the gradient of your classifier. And essentially what I would like to establish is a completely new view on guidance, namely as guidance as a kind of stochastic optimal control. Now, as follows, I want to build on an analogy that kind of gives you some intuitive thinking about what this paper is all about. And the intuition that I would like to convey here is that uncontrolled diffusion, so just sampling from your diffusion process, is a little bit like shooting a rocket from Earth into space randomly, right? So why is that? Let's imagine you just shoot a rocket into space, right? And it will just maybe end up at a random planet eventually, right? And so you have absolutely no control what that planet will be, right? So the idea is that this rocket is a stochastic process, right? And it obeys the laws of physics, but there's also a little bit of noise to that, and the outcome is kind of a random planet that this rocket will basically select. So here the planets are these sort of geometric shapes, right? So basically the rocket itself is the pre-trained diffusion model, right? And the sample trajectory of our diffusion model is the path that the rocket takes. But now imagine you want to control the rocket, right? You don't want to randomly end up at a planet, but you want to only hit like these triangles. So in other words, you have to eliminate a lot of these possible trajectories here. And in rocket control, this is done by a technique called thrust vectoring, right? So you kind of literally push and pull the rocket, using small jets, right? And this way you steer the rocket into the desired behavior. And this is actually working really well nowadays, right? You can actually land a rocket safely back on Earth, and the technique behind that is, of course, thrust vectoring, right? To a very fine-grained degree. So we want to go from this kind of uncontrolled rocket to the controlled rocket. And we want to essentially do the equivalent of thrust vectoring over the trajectory of the diffusion process to ultimately get a generative model that achieves our final terminal goals in a much better way than if you just do the naive thing, right? And to kind of find a mathematical notation for that as follows. I will think of the uncontrolled diffusion process or the uncontrolled rocket. I will call that Q, capital Q, right? That's my stochastic process. And my guided process or controlled process, I will call P. And now you might think, okay, before I get into all of the math, what are the two criteria that this approach really cares about? It turns out there are two goals that we should have in mind. And it's, again, like this nice analogy to what I just talked about in terms of rockets. The first thing is, of course, we want to kind of generate an image that we like, right? That satisfies our guidance cost, or that minimizes our guidance cost. So in other words, we want to be close to the target distribution for whatever we care about. But then at the same time, we don't want to deviate too much from the uncontrolled diffusion process. We don't want to push it too hard or too abruptly, right? Because that would basically generate that would kind of leave us out of the comfort zone of the diffusion model. It might kind of create crazy artifacts if we do that, right? So we don't want to do it too extremely. Okay, so filling you a little bit into the details, although I have to be fairly brief here, there are basically a couple of steps involved. The first step is, again, to specify the mathematical notation. I said the uncontrolled diffusion model is actually capital Q. And since this is an autoregressive model over time, right, where time indicates the diffusion steps, this can be written as a product of a small q of xt minus 1 given xt, right? Like the reverse model that starts with high noise and successively denoises it. And the model that we would like fit to the data is, again, capital P, and that is also an autoregressive model, P of xt minus 1 given xt, but then it also has an additional input ut, and that you can think of as the thrust vectoring force, right? So basically that is the control that we exercise in every denoising step in order to steer the behavior of that diffusion model. Now, in order to quantify these two requirements that I talked about in the previous slide, namely being close to the uncontrolled process and still maximizing a terminal reward, we then actually come up with a cost function that has the following form. It's a function of the data, and it's a function of these controls. And now there are two terms to that. The second one is a KL divergence between these two processes. And that actually assures that we don't deviate too much from the prior dynamics, right, as I just described, to kind of stabilize the diffusion process, if you will. And the second one is an expected terminal reward. So basically, this is an expectation under the terminal state x0, the noise-free image being sampled under the model. And then phi of x0 is basically, you can think of that as the negative log classifier, right? If you do classifier guidance, right? But this time over the noise-free image x0, right? But it could be any other guidance costs that you care about. You know, we'll see examples of that later on. And now what you optimize is this weighted combination with a WT weight, right? That you can steer between these two different behaviors, right? I mean, staying close to your untrained model, to your pre-trained model, or kind of terminate, or satisfying the terminal cost more. And it turns out that there's like a final approximation that we have to do, right? It turns out that this expectation here, again, has no analytical form, and it's actually very expensive to simulate. You could actually sample from the diffusion model, but then you would have to sample multiple times in every gradient step. So you would basically have an inner loop, and we want to avoid that. And so instead, what we do is we basically use Tweedy's formula here that gives you, instead of having an exact expectation under this conditional distribution, you plug in the most likely sample, right? So the expectation of x0 conditioned on xt and your current controlled force ut. And so we just call that phi of x hat. Okay? Okay. So hopefully you believe me that these are sort of the three ingredients. And of course, there's a little bit of math to it, and you have to kind of derivate all the formulas. But this is basically the final variational objective. It turns out that the KL divergence resolves into something very nice because we all deal with Gaussian distributions. And so the KL term basically has a closed form expression. Okay. Yeah. What is the intuition behind this algorithm? Well, it might be good to think about like a one-dimensional sort of toy case here, right, that you see on the slide. We have a denoising process here shown on the slide, right? On the left-hand side, we have maximum noise. On the right-hand side, we have zero noise. So this here is a distribution over images. And to make it look non-trivial, I just kind of selected it to be sort of a bimodal distribution here, right? And on the left-hand side, you have a standard normal Gaussian prior, which is indicated as a normal distribution. Now, what you would naively do if you do classifier guidance is you would follow, using, for example, DDIM sampling, you would follow these sort of deterministic trajectories once you selected the initial noise, right? And then you would actually be guided somewhere in this data space. but very often in many cases, due to these aggressive approximations I talked about, you actually not converge to one of the modes of the data distribution, but rather you kind of converge somewhere in between modes, right? So the model tries to find like a compromise. And as a result, turns out that the artifacts that you generate are pretty severe, right? This is a real application where we have some nonlinear deblurring here that we try to do. And this is what like the naive denoising posterior sampling algorithm, which is basically classifier guidance for inverse problems, would give you. Right? On the other hand, what the orange curve here shows is the nested algorithm that we propose. And this basically combines iteratively a denoising step and an optimization step. Right? In the optimization step, we sort of try to optimize this elbow evidence lower bound objective with the KL divergence that I showed earlier. So we search for the optimal thrust vector, if you will, UT, right? And then we move the diffusion process a little bit into this direction. And what it will empirically do, it will actually break the posterior symmetry and it will kind of kick you into one of these modes more rapidly so that you actually eliminate some of these artifacts, right? It's a little bit more expensive because you kind of iterate between an optimization algorithm and a denoising algorithm. But it turns out the optimizer only needs typically 2 or 3 steps to converge. So in practice, it's about 5 times slower, maybe, than a standard diffusion process. But that actually gives you much, much better qualitative samples, as I'll show you in a moment. Are there any questions at this point? Yeah, what's the format of the U? So everything I said was very abstract. So you can think U as something that you add to your noisy image to correct for it, right? It has to be a vector of the same dimension as the image. So it basically looks like an image itself. And this is actually what you see here. So basically, you kind of optimize for these U's, and the optimized U's are shown here, in every iteration. So what you see is that you very early on, much, much quicker than usually, you would kind of interpret these patterns, right? And then as time progresses, the role of the U's kind of get less and less important, right? It kind of really allows you to converge on a mode or to make a selection for whatever you generate at an earlier iteration effectively. Yeah.
Mm-hmm. Sorry, there's a follow-up. Then what is the phi?
Yeah, the phi is your so-called reward function or your terminal reward. So this is like inspired from reinforcement learning, right? Because there are these interesting connections here. But the easiest to think about is if you do classifier guidance, right, for natural images, then phi could be your negative log classifier, right? Your negative log p of y given x. Okay. But of course, if you solve other inverse problems, it's basically it's always in relation to the degradation operator that you apply. Yeah. All right. Yeah, to show you some qualitative results, they were actually fairly impressive, and to my knowledge, they're state of the art, at least as of summer 2025. So here you see a bunch of reference images, right? And then we applied a degradation operation on them. In this case, they're like a nonlinear deblur, which is sort of not completely trivial to resolve. And then finally, and now we tested against like a bunch of algorithms. On the rightmost color, this is like essentially the denoising posterior sampling or DPS method, which is the most naive thing that you can do. It's like relying on this point estimate of the convolution that I pointed out earlier. And you see that this algorithm gives a lot of artifacts, right? Then the red diff is a fairly recent NVIDIA algorithm from 2024, right? This actually carries out like some more sophisticated posterior approximation, but it's still like doing variational inference and but sort of a different kind of variational inference. And as a result, it is much better at artifact removal, but it still has like significant artifacts in there. And then finally, this algorithm here highlighted in red, that's our method. And you see that the results are much, much better. Actually, here in the video, the quality is not even as high as if you go into the paper. So it's very surprising how many details you restore, but if you pay close attention, there are still some artifacts that don't agree with the original image. Yeah. Okay. And here on the right-hand side, I have like these formulas that are being used, right, for solving inverse problems. How does phi of x look like? Well, it's basically a mean squared error between your lower resolution image or blur-free image and your blurry image and the blur operation applied to your current iteration of your diffusion model, mean absolute value, right? So you want to. Yeah, you want to find the image x0 that if you blur it, you end up in y, which is your blurry reference image, right? So, and that's like the additional loss function that you put into your diffusion model. Yeah, I'm not going to bore you with numbers, but we're doing fairly well. You can also apply the algorithm to other inverse problems. For example, stylization is a popular one, right? Where you have a feature extractor phi of R. Sorry for the clash in notation. This is a different phi this time, but this is a feature extractor. And you extract features from a reference image. You also extract feature from your current image. And again, you build a mean squared error. So you want the features to match, right? And then you use that for guidance. And you also get like state-of-the-art sort of stylization results on your images. Okay. Okay, so this kind of pretty much wraps up the first part. If there are no immediate questions, or if there are, I'm happy to take them. Otherwise, I could also, yeah, please go ahead.
I'm curious, like, how much does your spread change once you, like, with your algorithm versus like specifically like your spread in generated images, like compared to just typical diffusion? Like, does it limit it quite a bit, or like how narrow is your range?
I see. So you're basically saying that if I apply these techniques with spread, I mean, I guess you mean like how much sample diversity is there left, right?
Yes. Yeah.
Yeah. Yeah. This is a very interesting question. I believe we did not test this systematically. It clearly also depends on how much weight you put on the restoration term, right? The terminal cost. And there's a trade-off oftentimes between sample quality and spread. I should say that these methods are not really made yet for getting calibrated posteriors. We have some follow-up work that addresses that question specifically, right? But for now, at least it's kind of giving you another tool in the toolbox to kind of get essentially, yeah, higher quality artifact removal, if you will. Yeah. All right. So let me go to the second part of today's talk, which is about sort of heavy-tailed diffusion models. And this is work in collaboration and heavily inspired by my student Kushagra Pandey, who did this during his internship at NVIDIA. So what's the goal here? The goal is that in scientific imaging, in particular in weather and climate, we oftentimes deal with these, image-like data, but they're not really images. They're really they're really data points where we do care about the statistics, right? And we really want to get the statistics right. I already briefly alluded to that before, right? You have these rain areas. There's some intense pockets of rain. They're also very sparse, right? And essentially, when you just marginalize over the pixels and you look at the aggregate distribution over precipitation, you really want to get the heavy tails right. Because if you don't do that, then the model will fundamentally underestimate your extreme risks and potentially catastrophic consequences. So yeah, these maps are image-like, but heavy-tailed. And the generative workflows are basically, they're getting a lot of traction from industry, but so far there's been very limited attention paid to these scientific images with heavy tails. So the first experiment that we did was to actually see, how well do traditional diffusion models actually capture heavy-tailed statistics. Now this is a kind of typical two-dimensional, toy data set that people look at, right? It has like this funnel-like structure, and then the density spreads out in the top region. You can also look at the marginals, when you collapse along the X or Y direction here on the right-hand side, and you see it's like heavy-tailed, in particular the top marginal. And the question is, how well do diffusion models capture the statistics? And at first you might think, okay, diffusion models should be, in some sense, universal distribution approximators, right? If they're deep enough and if you have enough iterations. But how well does it work in practice with finitely many iterations and not infinitely deep networks and finite trading data, and so, et cetera, et cetera? And it turns out they're not very good at it, right? As you see here on the right-hand side. So here the dark blue are generated samples from a diffusion model trained on the data. And while it does capture the mode of the distribution, you can clearly see that it sort of suppresses these sort of tail outcomes, right? And actually that is also true if you apply it to actual precipitation data, right? So this is a real problem. So the question then is, can you design a generative diffusion model that has like the heavy-tailedness strictly built into the model itself? And surprisingly, this is possible and relies on some fairly elegant math that ultimately works. So for that, I have to go a little bit more into the technical depth. So what is a diffusion model really trying to match, right? So it tries to match two particular distributions that appear in the derivation of diffusion models. So on the left-hand side, you have a standard Gaussian diffusion with no learnable parameters, right? And you look at a very particular posterior distribution or conditional distribution, namely you're interested in the distribution Q over the slightly less noisy image xt minus 1, conditional on the noisier image xt, but also knowing the ground truth x0. Right? So it turns out that this here can be computed in closed form because for Gaussians, any marginalization can be pretty much computed, right? So this is a closed form expression. And then the model that you fit to it is a learned model with parameters theta that also predicts the less noisy image xt minus 1 condition on xt, but that does not have access to the ground truth image, right? And of course, you need that in order to do sampling, right? Because here, there's no way to kind of sample data from the ground truth diffusion model. So the right model lacks some critical information, and that's important, right? Now, why was the KL divergence chosen in the first place? Well, it's mainly chosen for computational convenience because if you work with KLs and Gaussian distributions, then everything has like closed form expressions, and the resulting terms are, simple formulas that you can straightforwardly optimize. But what we want to do here is instead of working with Gaussians, we want to work with conditionals, which are actually heavy-tailed. In particular, we want to work with student T distributions, right? So what are those distributions? Well, at first, they look pretty much like Gaussians, but they have a tunable parameter gamma. And the gamma parameter essentially controls their heavy-tailedness, right? So for gamma being infinity, you converge to a Gaussian. It's what you see here in the black line. But then for smaller values of gamma, you kind of get more and more heavy-tailed behavior. Now, it turns out that, well, the first idea is straightforward, right? I mean, what if we just plugged in these heavy-tailed distributions, the student T's, and can we just reinvent or redo all the math necessary for deriving diffusion processes, right, from scratch? Okay, so now in this case, like the first Q, you can in fact replace it with a student T distribution, and the marginals are still tractable, right, which is non-trivial. You can also parameterize a T-distributed learned distribution, right? And it turns out that if you replace the KL divergence, but by a different divergence measure, in this case it's the gamma power divergence, which I'm not going to write down here, but it turns out that this combination has a closed form analytical expression that actually results in a objective function with that you can tractably optimize. And so here's sort of the cookbook for that, right? The components are the perturbation kernel on the left-hand side. Traditionally this is a Gaussian, and then in this case it would be a T distribution with certain parameters, and you can kind of go through all the elements and all the ingredients in standard diffusion models and find the replacement for T distributions in the rightmost column. So beautifully, if you do all the math, and it's really a long calculation, the resulting algorithm is actually super simple. It turns out there's an algorithm for training and there's an algorithm for inference, right? And it just amounts to like an additional step, right? It turns out if you sample from a student T distribution, you can think of that as a two-step procedure. Because the student T is essentially a scale mixture of Gaussians, you first sort of select a width of a Gaussian distribution from a prior distribution over standard deviations, right? That's the first step. And then once you select it for that standard deviation, you sample from the underlying Gaussian distribution, right? And then marginally, if you kind of eliminated the first step, you would effectively sample from a student T distribution. And as a result, there's just like this additional step, right? You essentially randomize the standard deviations, and the rest is essentially very similar to what you did otherwise. Now, how well do these models capture, first of all, the toy data? What you see on the right-hand side is a particular fit, right, for with a heavy-tailed diffusion model. In this case, gamma was chosen to be either 4 or 20, and you see much better coverage of the tail statistics, right? You can see that particularly well on the marginals, right? That this really works. So we do capture tail statistics with finitely many diffusion steps. And then more importantly, it also works really well on actual rain data, right? So these are the images that the model was basically trained on. And when you then only look at the marginals, again, only on the aggregate distribution over rainfall, right? Intensity versus the value, the density, how oftentimes it occurs, and here's the intensity level of rain, right? The ground truth would be in green. The naive diffusion model would be here in blue, so it really cuts off the tails. And the heavy-tailed model here in red kind of really matches can be tuned in such a way that it really captures the heavy tails of that, of the ground truth data set. Just as an aside, you can also do with temporally varying inverse problems. This is not really drawing on the same methodology, but we also worked on video super resolution for rainfall. It's also an inverse problem, right? Because you observe low resolution rain signals, you want to kind of super resolve them. You want to do this in a temporally consistent manner. So this was done in conjunction with the Allen Institute. So we want to impose temporal coherence. We also want to have basically scenario generation that is stochastic on a high spatial resolution. And ideally also we want to get calibrated posterior distributions. And this works really nicely. And so what you see here is a cold front approaching the San Francisco Bay Area that you see here, right? This is the Bay. There's the Sierra Nevada right behind it, right? The reference signal that we condition on is this very coarse resolution kind of weather cold front coming in, right? Very pixelated. And then because the model is stochastic, you cannot only, you can actually super resolve it many, many times as you want, right? And you get an entire posterior distribution over high resolution scenarios conditioned on the low resolution reference signal, right? And this is basically what all of these columns do. Those are like temporal evolutions of different samples from the model. And the last one here is the spread among them, right? Maybe this answers also your question about how much spread there is, right? Now, this is still ongoing work to make the posterior distributions well calibrated, right? In this case, but that kind of gives rise to a lot of interesting future work. Okay. Any questions about part 2 before I move on to part 3? Yes.
On the previous example about the precipitation,
Uh-huh.
are you just getting the statistics of the precipitation likely from that coarse resolution model? Are you actually able to say this is where the precipitation will occur specifically?
Yeah.
Prediction, or is it just an estimate of the PDF?
That's a good question. So how much certainty do you gain, or how much do you just kind of approximate the CDF? You actually get a lot of, you actually do get a lot of better prediction, right? If you look at if you look at sort of the variation between these different stochastic runs, right? You do see small differences, right? But they're more or less agree to a very high level. For example, here you see very clearly this kind of cold front approaching, and this is like fairly consistent, I would say, across these different samples from the diffusion model. And if you compare that to your guidance signal, right, which is extremely rough, the model definitely has learned interesting things. Now, this looks a little bit like magic, but the reason why it works is that you also condition on geography, right? You put like mountain maps and so on into the model. And that is, of course, very informative, right? In particular here with the Sierra Nevada, right, can already tell you a lot about how a coarse resolution simulation is to be interpreted on a local level, right? But then the other question is, do we get enough diversity among these different simulations, among these different playouts from the diffusion model? Now that's a different level of uncertainty, and that I think might not be well calibrated. So that we didn't study very systematically at this point. Yeah.
What temporal scales are you guys conditioning on for the generation process? Like,
I think it's 3 hourly or 6 hourly. I think 3 hourly. Yeah. Mm-hmm. Okay. Okay. All right. Let's go to the last part of today's lecture, and I think we're just about right in time for that. Remember, the last big topic I wanted to touch on was this issue of uncertainty, right? Diffusion models are oftentimes poorly calibrated, right? In other words, the posterior distribution over plausible high-resolution images compatible with a low-resolution image, for example, are not really corresponding to the actual posterior distributions. In other words, there could be more variety in reality than what the model sort of assumes there is. And of course, calibration, which is the scientific discipline that cares about uncertainty, and is very established in supervised models. So there's a huge literature on calibration and different kinds of uncertainties in supervised models. But there's very little, or almost nothing, or arguably probably before our work, there's not a single work that I'm aware of that dealt with calibration in diffusion models. And so this still remains kind of critically underexplored. And of course, this has something to do with the fact that when you only care about generating nice looking images, you don't care about it, right? But if you do science, I argue it's very important, right? So yeah, this kind of remains dramatically underexplored. But what does calibration even mean for generative models? That's even that is a little bit unclear. So for this, we have to go into a little bit more detail. And I want to remind you, or if you haven't heard about it, teach you for the first time of like two different kinds of uncertainty that statisticians like to talk about, right? So one is the aleatoric uncertainty. And this is basically the intrinsic data stochasticity, right? This is just like the irreducible error that you just cannot eliminate when you make a prediction, right? You can think of this as rolling dice, right? And the outcome is just intrinsically impossible to predict. The other part of uncertainty is the epistemic uncertainty, also called the data uncertainty. And this is actually your uncertainty due to a model, in your model, due to, for example, limited data, right? If you have more training data, you might be able to eliminate that kind of uncertainty, right? If you just see more variety of data points, you can actually typically reduce the epistemic uncertainty. And the picture that I like to think about that is like this foggy image, right? Maybe if you take the image of the same castle multiple times per day and under different conditions, different angles, you can ultimately remove a lot of the uncertainty that that particular image instance still has, right? Okay. It turns out that you can actually nicely distinguish these types of uncertainties in diffusion models. But before I can explain that, I want to briefly talk about a particular posterior approximation that's been very popular in supervised models, and this is the so-called Laplace approximation. So what's the Laplace approximation? The idea is that there are many different posterior approximations that exist. And the Laplace approximation basically says, okay, I have this highly multimodal, complicated posterior distribution, but to the best possible way, I replace the posterior by a Gaussian distribution centered around its most likely value, and then with a standard deviation essentially capturing the uncertainty or the curvature around this point in the Hessian of your loss function, right? And so this kind of then is a measure of natural uncertainty in the model, right? I mean, how much can you wiggle your parameters and still more or less do the same prediction, right? If you cannot wiggle at all, then the model is very, very certain about the parameter configuration. But if you change the parameters a great deal and your prediction doesn't change really well, then your model is fairly robust and your posterior is very broad, right? So that's essentially what you do in Laplace approximations. And once you have made this Laplace approximation, which you can actually do when you optimize your model, but then compute the Hessian around the optimum, then you can basically sample multiple times from that posterior, and you get a family of model that all differ a little bit in their weights. This is actually illustrated here. And you can just build a big ensemble, right? And this ensemble then eliminates a lot of this sort of unwanted uncertainty that's remaining, right? So you integrate out over things that you're uncertain about, you average, or you kind of pool the predictions of many models. And so that's like a popular approach to do in supervised learning. So yeah, this enables efficient Bayesian ensembles. And in diffusion models, well, you don't have typically the supervision, right? But you still can do the Laplace approximation of your denoiser, right? So instead of just learning the most likely parameters of your denoiser, you also compute its Hessian. And then you, again, sample from that resulting posterior distribution, and you get an ensemble of denoisers, right? And that ensemble prediction should tell you something about the model's epistemic uncertainty. So this is actually illustrated here in this image. So here you have a single noise image, right, that you would start your diffusion sampling from. And what you see here are three slightly different denoisers, right? They all differ only in their last layer for computational practicality. And basically, what we did here for the last layer is we actually randomized or slightly perturbed the parameters in the last layer to make the models different. And the way we sample those parameters was based on the Laplace approximation, right? You can think about like taking the diffusion model, take the last layer, perturb it slightly, and then compare these different models. Now, what exactly did we do? We fixed the random seed to generate the initial noise, the initial randomness, and then we pushed the same noise through these three different diffusion models, and looked at the different images that these 3 different models generated. The idea was that if the difference is small or even unperceivable, right, then probably the model is very well probably the model is sort of well calibrated, right? Doesn't really differ much, and the model is at least very certain about like its output, right? It can be with high confidence, it can say how the corresponding correct image looks like, right? And that's actually shown here. Now, how do you measure the discrepancies between images? It's oftentimes easier if you don't do this on a pixel level, but if you go into a semantic space, as shown here, and then essentially measure the closeness of these corresponding embedding vectors in a semantic space. So this would be an example of low discrepancies. All these 3 different perturbed models more or less generate the same image in this particular example. Yeah? Now here's another example, again from the real world. If you just select a different initial noise image, push it through the same 3 different models, sometimes you're unlucky or something else happens, right? And basically the images that you generate look very different, right? Here there's some weird sort of hybridization of a dog and a woman, right? And basically, yeah, I mean, clearly here, a small perturbation of the model's parameters lead to drastically different outcomes. And this is bad, right? I mean, this is not what we want, right? When we use diffusion models in climate science or weather forecasting, and you have this sort of lack of robustness, clearly there's something you cannot trust here, right? The model about, right? Again, you measure it by kind of taking these 3 images, you go into a semantic space, and essentially look at the entropy or like how much discrepancy there is between these embedding vectors. Now, what we found is essentially this measure of confidence, right? It's actually an intrinsic measure of confidence of this ensemble of models, very strongly correlates with sample quality. So in other words, when you end up hitting a noise sample that results in very differently generated images, right? Then typically those images are also very bad, right? Subjectively speaking. And when you hit a noise sample that generates almost the same image, then also the image quality itself is very high. Now how can you quantify image quality? It turns out there are all sorts of metrics you can look at, like FID is one example, right? By the way, this is mostly for natural images. For scientific applications, you have to come up with different measures. But again, we found that there's this very strong correlation. And why is that interesting? Well, it's interesting because now you have sort of a measure for model performance without reference to any external data sets, right? You can just generate an image, and without comparing that image to any reference distribution, you can immediately tell if that image is likely bad or good, right? And if it's bad, you can just like sample again. You just discard the sample, sample again. Maybe next time you're more lucky, right? And you generate something else that actually does not show discrepancies, right? Yeah. Okay. Yeah, so this is kind of accepted at UEI. I think there's a lot of interesting work you can do as a follow-up out of that. Actually gets me to the end of my talk. Yeah, I talked about diffusion models that are evolving from image generators to tools for scientific inference. At least I believe that this is giving rise to a very interesting methodological research agenda that sort of bridges natural sciences with computer science very, very nicely, and gives you sort of new ideas that are maybe less explored in industry. So if you're like a PhD student and you're interested in topics, you're worried about competition from Google and Meta and who else, right? Those are probably questions that these big tech companies are likely not going to answer, right? The key capabilities I cover today are 3 aspects to that agenda. One is control, to kind of essentially think about how can you do guidance better. And there we kind of made this interesting connection between stochastic control and how it connects to guidance in diffusion models as a new way of doing test time adaptation. I talked about expressivity of the expressiveness of the learned distributions by looking essentially at the tail statistics. And here these sort of heavy-tailed models are still very underexplored. I'm not sure that there's actually a lot of follow-up work yet, although I think it's an extremely useful technique, in particular here in our domain. And then lastly, I talked about uncertainty, and that is like a huge open-ended problem still, right? I mean, again, very much something that scientists care about, and maybe people in imaging less so, right? And there I talked about a method that uses a Laplace approximation from Bayesian statistics to generate ensembles of denoisers and to use the discrepancies of the denoisers as a confidence map for the quality of the generated sample. So yeah, overall scientific models must provide efficient inference, calibrated uncertainties, and get the right data marginals. And yeah, that's the end of my talk. Very happy to answer any questions. Thank you.
So thank you, Stefan. Very impressive. So my question is, what are the theoretical implications of performing this diffusion process in a latent representation, in latent space, instead of performing directly on the original space?
Great question. So yeah, the question was about like latent diffusion and what the theoretical implications are, in particular when it comes to, I guess, questions surrounding calibration also of these models, right? Yeah. I think it's a very ad hoc method, right? I mean, I think I have to think a little bit more about it, but my first answer is that because you're first doing compression, right? You first apply an autoencoder, you ultimately diffuse in a much lower dimensional space than your original data space. I think you probably already eliminated a lot of the rare events or things that the model doesn't think it's sort of important enough to capture, right? So I would be a little bit skeptical, although it's something I never sort of studied, rigorously. That's one thing. The other thing is that a lot of people use sort of latent diffusion in various contexts for, right? But you have to remember that this is actually a very specific model that was generated for natural images, right? Because it does have an autoencoder, but then there's also an adversarial term that was used to train the autoencoder in order to make sort of more perceptually pleasing image patches. And whenever you have a GAN loss involved, you're heavily biasing your result because the GAN really is almost designed to break posterior modes, right? You kind of select a mode rather than average over them. And that is actually another source of potential underestimation that might occur. So maybe for scientific context, we might have to train our own. I mean, for sure, we need to do our own sort of latent diffusion. But yeah, I'm not aware of any sort of systematic work on it. It's interesting.
Thanks for this fantastic talk. So I want to discuss something about control. So I'm doing some data simulation, right? But I think in the computer vision to generate a picture, the guidance, the solution could be really spread out. For one guidance, for example, generate a cat picture, so you can have many solutions. But for data simulation, you only have one optimal solution, right? So in my practice, so I find that it's hard to control using the observation. You have to care about the parameters, super parameters for the guidance and something. So what do you think about this?
Yeah. I guess the comment is that it's sometimes hard to control I guess in data assimilation particularly, right? Because sometimes your signal is very sparse. And we actually made very similar observations also for, although you always see these sort of amazing results for solving inverse problems like super resolution, deblurring, inpainting, oftentimes they're only really good when your reference signal is fairly high dimensional still, right? I mean, for example, if you do factor 2, factor 4 super resolution, you still have like a dense image, right, that to condition on. But I guess in data assimilation, particularly when you work with weather stations, it's basically like having like a handful of pixels that are active and all the rest is very sparse. And for those cases, in a fully different context, we made similar observations that sort of solving these inverse problems is actually very hard and requires a lot of parameter tuning. There might be very particular annealing schedules that work. I don't think there's like, I'm not aware of like, any research paper that focuses particularly on these extremely sparse inverse problems. I agree. It's very interesting. Yeah.
If I can, maybe you may also want to check the preprint that we published on arXiv a few.
I think this is a public talk, so I probably cannot. Oh, arXiv. Sorry. Okay. There might be interesting follow-up work coming from this group, so stay tuned. That's all I'm saying. But thank you.
Yeah, I was just wondering when you're showing the heavy-tailed experiments, does new need to be specified? Is that a hyperparameter, or can you learn that?
That's a great question. Yeah, in this case, because it's sort of a collaboration with NVIDIA, I'm a little hesitant to say too much. But in this case, it's a hyperparameter that is just picked, right? But in principle, you could also learn it. Yeah.
Okay, thank you so much.
Yeah, thank you.